video, we are going to use the Excel solver in order to solve some common problems that an engineer might encounter, like equation solving and also fitting of experimental data. So let's begin with the equation solving with the Darcy-Weisbach equation as a starting point. So this equation gives us the pressure drop between the inlet and the outlet of a tube which is filled with a fluid in forced convection. So this pressure difference is given knowing the length of the tube, the hydraulic diameter of the tube, the velocity of the fluid, and the density of the fluid, and a friction factor named Fd here. The friction factor can be estimated by a lot of correlations depending on the flow regime, like turbulent or laminar, and also depending on the surface of the tube, like if it's smooth or not. In this example, we just use the Kalman-Prandtl correlation to estimate the friction factor for turbulent flow and smooth pipes. So this correlation gives the friction factor for a fixed Reynolds number, and as you can see, you cannot isolate the friction factor here on one side of the equal, so you need to use a tool for find the value of Fd which solve this equation for a fixed Reynolds number, or in this case, because you have only one parameter, you can also plot this equation and find the solution with a plot. But for this video, we will try to do it with the Excel solver. You can also try to do it manually with an iteration process. So first you fix first value of Fd and you check if it resolves the equation, and if not, you change the value of Fd, and etc. So this could be really difficult to do if you have more than one parameters, and this is why we are going to use a solver here to illustrate how to use it, because it's very efficient. But the Excel solver, and usually all the tools that you can find for doing these kind of things in different programming language like MATLAB or Python, usually these tools only make you able to minimize a function. So usually you have to transform your problem in order to have a minimization problem. So here in this case, in order to have a minimization problem, only we can put everything on the same side of the equal and take the square here. So we make the problem only positive or zero, and so if we try to minimize this, we will reach zero if everything is fine. So the square is not mandatory. You can take the absolute value or other things, but the square is good practice. And you have to now to enter this formula in a cell. It will be our objective function to minimize here. So I enter the function here, 1.93 log 10. B4 is a Reynolds number, that is a constant here at 10,000 to be in turbulent flow. And here you have the racine, the square root in French of E4. So the friction factor is given here in this cell, minus 0.537, and again the square root of E4 and all of it squared. So here the objective function is given, and it depends on the value of this cell. So you have to set an initial value here, and we will talk about the importance of this initial value just after. But for now, let's just try to minimize this problem like that with this initial value we set with a very arbitrary value. So to use a solver, you have to click on Data tab. I think, sorry, my Excel is in French. I believe it's the Data tab in English, and click on Solver. And here you have to set the objective function. So here my objective function is on C4, and I want to do a minimization. So here Excel propose to do different things. You can maximize, you can also try to find a specific value, but again, it's a very good practice to do minimization, because usually other tools that you will find with programming language will do only minimization. So here I want to keep it more general and do a minimization. And after you select the variable cell, so here we have only one cell that the solver can act on it in order to influence the objective function and try to minimize the objective function here in our case. I don't put any constraint and I remove this because I want to let the solver completely free and even put a negative value of the friction factor, you will see. And we can change the algorithm that the solver uses. So you have the GRG nonlinear, which is the default algorithm for a smooth problem. You have the simplex PL for linear problem, and if you want to use it on a nonlinear problem, you will get an error. And you have the evolutionary algorithm. So just as a good practice, the evolutionary algorithms usually are more performant when you have a lot of parameters. Let's say, for example, something like 10 parameters or more. It could be very interesting to use an evolutionary algorithm, but again, it depends on your problem. It depends on the algorithm. But it just to keep in mind that if you have a lot of parameters, you can try the evolutionary algorithm and see if you get a better solution, or if you reach a solution faster. So you can try it. And also it's interesting for non-smooth problem. So here we just take the nonlinear because it's a very simple problem, and this algorithm usually perform quite well. So here, if I click on solve, I see that my solver doesn't converge with a satisfying solution because the friction factor is negative, and so the my function is not defined for a negative friction factor. So I'm clicking on cancel to just keep the initial value here of the friction factor. So now let's try to help a bit the solver by putting a constraint on this this variable and make it only positive or 0. Okay, so non-negative. So here, if I click on solve with the same initial value, the solver again throw an error, and it shows a 0 value for the friction factor, and so again the function is not defined for a 0 friction factor. So again, the solver is unable to converge here, even on a very simple problem like that. So I click on cancel and again start with the same value, but I'm going to help the solver by giving a lower bound for my parameter. So how to set the lower bound? So here comes the expertise of the user. That means the solver doesn't do everything. As we can see here, it can't converge in very simple problems. So here you have to know a bit about your problem you want to solve. So you have usually to use consistent value of the initial point, we will see that just after, and also consistent value for lower and upper bound. So how to find the consistent value here? First, we don't want the objective function to be undefined, so we know that the friction factor cannot be negative or 0, so we could put something like just above 0. I think it's what we are going to do, but we have to check that this value, this lower bound, is lower than the expected value. So here it's easy because we know our problem. If I just take the Mundi diagram given here in Wikipedia, we have the friction factor is here is given on as a function of the Reynolds number. For smooth pipe, here it's the pink curve, and for 10,000 of Reynolds number, you can see that we have a FD around 0.3, okay, 0.1, 0.2, 0.3. So we are expecting a value of FD around 0.03, okay? So we can put here a very low value just to avoid 0, and we know that here we will be below the expected value, so it's okay. So now I'm going to add a constraint here. So to add a constraint, I have to select the variable cell and set that I want to be upper or equal to the constraint. Here, for example, and I click on OK, and here if everything is fine, it just puts the constraint here e4 upper or equal to f4, and we can remove this option because it's not used anymore. And here with the same initial point, we click on solve, and this time the solver is happy. It says that everything is okay, it converged, and we are also very happy because he found an expected value of 0.03. So in this case, again, very simple problem, we know the expected value. And just to check, to be completely sure, as I said at the beginning, with this simple problem with only one variable, we can plot the objective function as a function of the friction factor. So I did it here just to see, so the objective function versus the friction factor, and in this domain here with the friction factor going from 0.01 to 1, we can see that there is only one minimum, and the minimum is around 0.03 for the friction factor. So here we are very happy, the solver is doing well when he found 0.03. So let's save this optimization options here, just to show you how to save it, because we will use that functionality after. So to save, you just have to select one cell, and Excel will write things below this cell. So you click on save, and Excel writes some things here. So here it tell Excel the objective function, and it's a minimization here. And here it tells Excel where is the objective parameters, and the number of parameters. And here it tells where are the constraints. You can see they are written directly here. And here you have a lot of parameters, and boolean, faux is for false, and vrai is for true, so true and false boolean here, and some values. So here, unfortunately, Microsoft doesn't give any documentation on that, so we can have a very limited use of this. But if you try to modify some value, you will find that you can modify, for example, the solver which is used, things like that. But personally, I just use that for adding constraint. I found this very useful, very straightforward. To add a upper bound constraint, for example, I just have to do this and this, and I have a upper bound function, for example, let's say 0.5 to have a true constraint. Okay, so I'm going to launch this optimization just after, but here let's try with another starting point, for example 0.6, so something closer to what we expect. So here we assume that we know a lot our problem, and we know that the value will be close to that, and you give very consistent initial parameter. And here we can try to remove the constraint, okay? And so we do exactly the same first solve with no constraints, and just the variable size and the objective function set and the default nonlinear algorithm. But this time we have changed the initial point, and here if I click on solve, it found the good value, the expected value, and he is happy and we are happy. So here, to illustrate really the importance of the choice of the initial parameter, again, you need to know your problem. Unfortunately, if you have a lot of parameters, it could be really tricky to find a consistent value for each parameters, and for the global population of parameters. And you can have problems to find a good minimum. So here I want to talk about the notion of local minimum and global minimum. So here it's plotted a fictive objective function. You can see that there is a minimum here, and depending on the initial point, you can have your solver here sticking here and converge and say that everything is okay for him and just give you a solution. But you can see that in the domain, the function domain, you could find a better minimum here, which is called the global minimum here, because there is only one like that, and this is a local minimum. And if you use another initial point, maybe you could find the global minimum. So it could be very tricky to be sure to obtain the global minimum, and sometimes completely impossible. But a way to do that could be to choose different initial points, and for each initial point try to solve the problem. So you will obtain several solutions at the end, and you will have to sort the solutions. So for example, just take the smallest one, or you can also sort by parameters consistency. I mean, usually you expect physical interpretation of your parameters, and so you can also sort the solution with physical meaning of your parameters. And with the computer that we have today, you can do a lot of initial points, starting points. So for example, you can try with 10 starting points and even 110,000 starting points, and each time you use a randomly selected starting point. It's a method. You can try it if you are not sure, if you always stick on local minimum. You can try to take just random value of initial points in the function domain. So in order to do that, you have to set lower bound and upper bounds for each parameter, and just take a random value between these two bounds. And again, you can do that like 10,000 times. If your minimization problem is very fast, you can do a lot, and after you have to sort the solution obtained. But of course, it's a bit difficult to do that with Excel iterative process like that. But with programming languages like MATLAB or Python, is very easy to do. But again, it's just to point out the importance of the choice of the friction factor. So it could impact the convergence of the solver, as we can see. Even in a very simple problem like that, the solver was unable to find a solution, and also it could impact the way you find a global minimum or not. So before to go to the next part, just to show you how to load these values that I have said before. So you click this time on all the cells with something in it, and you click on load, and you click on replace, because if you mix values, sometimes it's doing very weird things and duplicate constraints. So I would recommend to always click on replace, and here you can see that we have all the constraints which are well written here, and we can click on solve, and of course we obtain the good solution because we don't need a upper bound in this example. But I want to really insist on that. Always put a lower and upper bound is a very, very good practice. It will really help the solver and give you more control of what you do, and increase the reproducibility of your results if you change the Excel version, or if you use in parallel programming language like MATLAB or Python. Is a very, very good practice to always put a lower bound and upper bound, and usually it's mandatory. The default Excel solver doesn't ask for that, but if you try to use the evolutionary algorithm and you don't put a constraint, a upper bound and lower bound, if I just put a lower bound constraint, if you try to solve this, you get an error, and Excel tell you that for this algorithm you have to set lower and upper bounds. But it's usually the case if you use this kind of tools in programming languages, again like MATLAB, Python, etc. Usually these tools needs lower and upper bound. It's mandatory. So let's jump to the next part about the fitting of experimental data. So the idea of the fitting is to find the parameters value of a model in order to fit experimental data. So it's a very common problem for engineers. So it's also called parameter identification. In order to do that, here I have to generate experimental data. So here I will generate just fictive experimental data, completely fictive, with x vector, fictive x vector, which is supposed to be experimental, which is assumed to be experimental, and a y experimental vector, which is calculated just with a second order polynomial here, a x squared plus bx plus c, with the parameter abc here. Okay, so I just generate a y x vector, and I just add some noise, some fictive noise, in order to simulate experimental data, and I end up with this vector. So this is my experimental data on the y-axis, and here my experimental data on x-axis. Okay. And I have to calculate my model. So my model is calculated in the same way here, because I artificially generate experimental data, but the model will be calculated like this, with again a x squared plus bx plus c, but this time the abc parameter can be changed by the solver. Okay, the Excel solver will try to change this value in order to minimize the error between the model and the experimental data. Okay, so I have to calculate, of course, this model value for each experimental x. So I use here the experimental x, of course, and not another x. And I have to calculate the error between my model and the experimental data. So it's a bit more complicated than the previous problem with equation solving, because here we have to calculate an error for each value of x, each y corresponding to one x. And after, we have to find a way to minimize just one value and not a set of value. So I will explain that just after, but we have to start with the calculation of the error on each x point. So in order to calculate the error, we will use the relative error here, with y experimental minus y model divided by y experimental. So this is very important to divide by the experimental value in order to again to obtain relative value relative to the experimental y, because if we don't do that, we can have, for example, here the y which is much higher than this one, and so we could have very different error between these two values, just due to the fact that the y is different at the beginning, and not just because we are less accurate or something. So if we divide by the y-x, we just ponderate all the y value in the same way. Okay, there is no some points more ponderate than others, all have the same ponderation. Okay, it's very important, the relative error. And here we multiply by 100 just to take the percent value, but the solver doesn't care about that, it's just for us. And after, I take the square again as the same as the previous model, just to obtain a positive value. And if we try to minimize this, it's like if we try to set it to 0. Okay, so now I have an error for each value of x, which is calculated here. So it's again yx minus y model divided by yx and multiplied by 100 to get in percent. And here I take the square error, but I have that for each value of x, I mean for each y corresponding to one value of x. And I have to generate with that just one value that the solver will try to minimize. So a very simple way and common way is just to sum up all the value. Okay, so just try to minimize the sum of the squared errors. Okay, but sometimes you want to influence the solver in order to be more precise on one range of x and less accurate in other range of x. So for that, you can sum, for example, just a part of the squared error and multiply by a ponderation coefficient, and add the rest of the sum multiplied by another ponderation coefficient. So just to say that you can make things quite complicated in the objective function. But here, making simple, just the sum of all the errors, so we doesn't ponderate any parts of the x vector. So before to launch the solver, we have to set some initial value for A, B, and C. And as I said before, you have to know a bit your problem. So here I have put some random value, but I have set A lower than B and lower than C because I know that at the end I should expect A be lower than B and lower than C. Okay, so it's quite random value, but with a bit of logic here. And here I have plotted the model value in orange and the experimental value in blue, and the relative error between both in gray here with the axis on the right, okay, in percent error. So let's try to solve this, and I will load some options already saved here. So here if I load that and I click on replace, no, it's okay. So here to check, I have the objective function in Q4, that is correct, and I have a range of parameters, this time not just one parameter but a range of parameters, and the solver will modify these parameters in order, and it will modify the y model here and modify the error here, the squared error, and so the objective function at the end. So by acting on this, the solver will act on the objective function. So if I click on resolve here without putting any constraint, it found the solution and it seems to be very happy. Everything is, all constraints are satisfied. It said that it is converged. Okay, so I click on OK. And just to see what it gives on the graph, you see that this time the model is closer to the experimental data. So here, depending on your problem and what you want to do, you will have to choose if the accuracy is enough or not, and if you want to do other things and try to obtain more accuracy by, I don't know, using a better algorithm, or try to choose over initial points. But if the accuracy is correct for you, you have also to check the physical meaning of your parameter if necessary, because sometimes we just have empirical models and we don't really care about physical meaning of the parameters. But if you do care about physical meaning, it could be here very tricky, because as you can see, the C parameter looks very close to the initial C parameter, but it's not the case for B and not really the case for A also. But here we don't expect really these parameters because I add noise on the Y value, so this parameter ABC doesn't exist anymore, and it's the case in the real life. Your parameters doesn't really exist in the real experimental data, and you don't know which value you really have to obtain, and so sometimes it's very tricky to obtain physical consistency of your parameters. Sometimes you just have to accept the parameters the solver give you, and but it could be very frustrating. But just to say that the solver doesn't do everything for you, and sometimes if the values are not consistent, sometimes you can just not use this value because you absolutely need physical interpretation. Just to say that it could be quite tricky, and even in this simple example here, we don't know what we expect exactly because there is some noise. So now let's try another minimization with constraint parameters with lower and upper bound. It will not change the results, but in this case it will not change the result, but just to show you a case where we put constraint on with several parameters and not just one, like on the previous problem. So I'm going to put initial values again for ABC, and I'm going to load some value that I have saved here. and I load and replace everything. And here, as you can see, I have quite the same problem to solve with Q4, N5 to N7, the same parameters, but I have added a lot of constraints here. You can see it could be a bit annoying to add all these constraints because I like to do it with directly in cells. But here we have constraint for lower bounds and upper bounds. So lower bounds are on K column and upper bound on L. So you see always upper equal to K, upper equal to K, and lower equal to L, L, L. It looks good. So here, if I click on solve, I obtain exactly the same solution, of course, because it converges also without constraint. But so we converge with on the same minimum. I don't know if it's the global minimum or not. Of course, we usually never know. This video is coming to an end. You will find in the description below a link to download the Excel file I used. And voilà, à plus, bye bye.